Yes friends, with the discussion on the feedback performance characteristics over, we can now switch over to the design problem, and I think the best we can do is to take up the lead and lag design through examples, because the lead and lag design through root locus method have already been introduced to you. You will recall a lead compensator has both the lead and the lag, it is a pole 0 pair. In the case of a lead, if you recall, there is a 0 followed by a pole, and in the case of a lag, a pole followed by a 0 as far as the left half plane is concerned. I think I can make this sketch here and you will surely recall that. This used to be the situation when we used to take up the problems on root locus method, a 0, a compensator 0, and at a sufficiently large distance used to be a pole. So it means if I consider this to be 1 over tau, this I can say it is minus 1 over alpha tau, naturally alpha will be less than 1, and the transfer function of a lead compensator, let me call it ds, can be taken as s plus 1 over tau over s plus 1 over alpha tau with alpha less than 1. Okay, I think let me go ahead with the lead compensation. I come to the lag compensation after the discussion on the lead compensation is over. We have seen in the root locus method as to how to place the 0 and the pole appropriately so that transient performance of the system is improved. That was the objective. We used to pull the root locus towards left so that it passes through the point which is our desired point, which is the point corresponding to the desired closed loop poles, and that point used to correspond to zeta and omega n. Now let us think in terms of frequency domain. Zeta and omega n, if they are specified, I will say that using second order correlations, these indices have been translated to phase margin, let us say MR, omega b, or equivalent indices. In my examples, let me take that the phase margin and kV and let us say omega b, these are the three important specifications, and any other specification could be checked whether it is met with or not. If the specification is not met, in that particular case you have to enter into the design cycle, you have to take another trial point, and using the new trial point you have to make the calculations again. So you see that I now want to go ahead with the design of ds, that is getting the values of tau and alpha so that performance requirements on kV, phase margin and omega b are satisfied. I like to say that in addition to the flexibility on tau and s alpha, I have the flexibility on the gain also. After all, I can put an amplifier stage with the compensator. So instead of saying that we have 2 parameters, we have in fact 3 parameters, Kc, tau and alpha. But as we did in the root locus method, what I do is the Kc parameter I take up with the uncompensated system. I will calculate the value, but I call it a parameter of the uncompensated system. The only thing is that once the parameters Kc, tau and alpha have been obtained, then at the realization stage I will see whether Kc is totally coming from the compensator or is partially coming from the plant itself and partially from the compensator. That will be just implementation. I have 3 parameters and Kc I take to the uncompensated system. In that particular case, I will say that I have a transfer function Kgs, so that the K parameter is available there for adjustment, and I have a transfer function ds, so that the parameters alpha and tau, I think yes, another change I make. Since I am now working in the frequency domain, please see I call it Kc tau s plus 1 divided by alpha tau s plus 1. This is more convenient for me. This is the gain Kc here. That is, I am writing the compensator transfer function in time constant form, because in the frequency domain that is more convenient. This Kc is not the same Kc, you can call it Kc dash. It's a different Kc, but still I take this Kc to be taken along with uncompensated system, so that as far as the definition of compensator is concerned, it has 2 parameters tau and alpha. Kc will be taken care of at the implementation stage. Therefore, Kgs, the plant model, and here is the compensator. and ds now I am writing tau s plus 1 divided by alpha tau s plus 1, and here is my feedback system please. Get me the values of k, tau and alpha so that the requirements on phase margin, bandwidth and kV, the velocity error constant are satisfied, or any other error constant, it depends upon the type of the system I am handling. Okay. So now first I will like to study the frequency domain characteristics of DS. Just this very example will take us to the design algorithm as well. Characteristics of ds. So let me write this as dj omega is equal to j omega tau 1 plus j omega tau 1 plus j omega alpha tau. Help me please, give me the magnitude and phase characteristics of this. Let us see how this is going to behave, what contribution this particular compensator is going to give to the Bode plot or the frequency plot of the uncompensated system. This is what I want to see. What contribution does it give? What way we are going to design the parameters tau and alpha so that we are able to shape the frequency response of the total system. So if I make the Bode plot sketch for this, this is omega, this is dB. Please see that in this particular case your magnitude is 1, so I go up to 0 dB here. What is the next corner frequency? It is omega is equal to 1 by tau, and here is a corner frequency, omega is equal to 1 by alpha tau. Which way I go please? Plus 20 dB or minus 20 dB? It is plus 20 dB because this corner frequency is because of a 0. So I take this way up to this point, and then here it becomes horizontal because the pole adds up a slope of minus 20 dBs per decade. So after this point it is going to be 0 dBs per decade. So I have omega is equal to 1 over tau, omega is equal to 1 over alpha tau, and this becomes the magnitude characteristics of the lead compensator I have with me. The phase characteristics, let us see. Omega, in this particular case, tell me please, help me, what type of phase characteristics do you expect? Since alpha is less than 1, your phase angle alpha is tangent inverse omega tau minus tangent inverse omega alpha tau. This is going to be your phase angle, and therefore in this particular case the phase characteristics will be of this type. Is it okay please? The phase characteristics in this particular case is of this type. This is your frequency here, the cutoff or the corner frequency, and the frequency here. You will note this is your 0 degrees. Please note why the name lead compensator has been given to this. It adds a leading phase angle. Here is a positive angle. It adds up a leading phase angle to the overall phase angle of the system you are designing. And this is the feature of the lead compensator which we are going to utilize in our design. This is the feature of the lead compensator. Well, couple of questions to you. Can you get me the frequency at which this angle is maximum? Let me say the maximum value is phi m. The maximum value is phi m, and the frequency at which it occurs is omega m. Let us try to get the value of this particular frequency. The couple of parameters which I will require in my design, I am taking your help to get those parameters. Phi m naturally will come from this phase angle. So what I am going to do is, I will take the derivative of the phase angle with respect to omega, that will give me omega m. I will substitute this omega m over here to get the value of phi m. Okay, let us do that. Phi is equal to tangent inverse omega tau minus tangent inverse omega alpha tau. Tangent phi becomes equal to, yes, omega tau 1 minus alpha over 1 plus, yes, alpha omega square tau square, please. This is the value of tan phi I am getting. Now let me take the derivative of this with respect to which parameter? I am interested in omega, with respect to omega, and set it to 0. So taking d phi by d omega equal to 0 from this equation gives me omega equal to omega m, the frequency at which the maximum phase angle occurs. and I leave this simple this expression to you to calculate. The value is 1 over tau into 1 over alpha tau under the root. You please recall what is 1 over tau and 1 over alpha tau. These are the two corner frequencies. So if omega m is equal to 1 over tau into 1 over alpha tau under the root, it means it is geometric mean of the two. You may please see 1 over tau and 1 over alpha tau. The frequency at which the maximum occurs, it is the geometric mean of the two corner frequencies. It's easy to remember that way. It's 1 over tau is this, 1 over alpha tau is this, multiply and take the under root of this. It is this frequency at which the maximum occurs, please. Now if I substitute this frequency in the phase expression, I will get the value of phi m, and let me arrange that phi m in this form. Sin phi m is equal to 1 minus alpha over 1 plus alpha. A simple calculation for you, please, to check. Sin phi m is equal to 1 minus alpha over 1 plus alpha. Okay, still manipulation of this is needed because I am interested in alpha. This can be manipulated to get me the value 1 minus sin phi m divided by 1 plus sin phi m, please. This is the value of alpha in terms of phi m. Phi m is the maximum phase angle, and I will be using this expression in my design. And please keep set in your mind as to how did I get it. I have taken the derivative of phi with respect to omega, and from there I have got the maximum value of phi and omega at which it occurs. The maximum value of phi in terms of alpha I get, I have manipulated this to get the value of alpha in terms of phi m, because this is in this form I know I am going to use the equation in design. Okay, so please see now one more calculation I want to take up. Can you give me this value? Come on, take a little time. You can take a little time and get me this value, please. What is the value of this magnitude? What is this magnitude? Yes, you see that as far as this factor is concerned, it is coming from 1 plus j omega t from the 0. As far as this line is concerned, or this plot is concerned, this plot is coming from 1 plus j omega t, and after this corner frequency, you in the asymptotic plot you have in fact neglected 1. So can I say that this particular magnitude dB is equal to 20 log 1 plus omega squared tau squared under root, and this has been approximated as 10 log omega tau only, because for omega tau greater than 1 I have neglected that one in asymptotic approximation. So it means as far as asymptotic approximation is concerned, the equation becomes dB approximately equal to 10 log omega tau. Now help me please, what is the value here? Take omega is equal to 1 by alpha t. So if I take omega is equal to 1 by alpha tau, this becomes equal to what? No, it will become 20 log omega tau. Please see, it will become 20 log omega tau because this 2 is coming here. So now if you take omega is equal to 1 over alpha tau, what is the value please? 20 log 1 by alpha. Is it okay? So I get here the magnitude as 20 log 1 over alpha. Now if this is this we have solved, give me the value of the magnitude at this point please. The magnitude at this point. Yes, 10 log. Please all of you verify. If I substitute omega m, this value here, I get the magnitude at this point as 10 log 1 by alpha. This is what I need as the information about the phase lead network, about this compensator before I take up the design problem. I summarize the information now that this is a phase lead compensator. A lead network will give me this value. It's an RC network or an op-amp circuit that can be taken to give me these characteristics. This provides the phase lead. The maximum phase lead occurs at omega m, which is the geometric mean of the two corner frequencies, and the maximum phase lead is related to the parameter alpha, and this relation is given by this. At this particular frequency, the magnitude is 10 log 1 by alpha. This is the magnitude, and the maximum value you are getting is 20 log 1 by alpha. Keep this in mind. If this is well set in your mind, in that particular case the design problem will quickly follow. There will not be any problem at all. Okay, and as a design problem, I take a situation of a type 1 system. Let me take this as the design problem. That is, your uncompensated system Js is equal to K over S into S plus 1, and the requirements are Kv is equal to 12 and phase margin equal to 40 degrees. Please help me. Kv is equal to 12 and phase margin is equal to 40 degrees is the requirement. There may be additional requirements on bandwidth as well, that we will check. But let us first meet the requirements on phase margin and system Kv. Now you see the steps, please. The steps will follow easily from the this example itself. I am not listing the steps. I will save time here because the example will make the steps very clear. The very first step I want to take. Okay, you design your K so that your Kv requirement is satisfied. Please give me the value of K to satisfy the Kv requirements. Then the value of ds I am going to introduce should not change the Kv of the system. That we have to keep in mind. Please help me, what is the value of K I should take to satisfy the Kv requirement? 12. And how about the effect on ds? Please tell me, whatever ds you take, will it change the value of Kv? Keeping in mind that your ds is tau s plus 1 divided by alpha tau s plus 1. Keeping in mind that your ds is tau s plus 1 divided by alpha tau s plus 1. It will not change. Please see, your Kv will not change. That is why your Kv is set once for all, and I am taking in this example Kv equal to K equal to 12. So one parameter is decided by Kv. So this decision I have taken on Kv. So now I have to take on the phase margin decision, and therefore I need the plot of the uncompensated system first. Gj omega equal to 12 over j omega plus 1. This is the value, and now please make a rough sketch. You know how to make it. 12 by omega will be a line of minus 20 dBs per decade, and this is a pole which will add another line of minus 20 dBs per decade. So this becomes the magnitude plot of the uncompensated system, with this as a minus 20 dBs per decade slope and this as minus 40 dBs per decade slope, and you know that this corner frequency is omega equal to 1. And I can make the phase angle plot as also. For this particular case, the phase angle, as you know, is minus 90 degrees minus tangent inverse omega. I am giving you the rough phase angle plot. At this frequency I want to get certain phase margin. So this is the phase angle plot. As you know, it will be tangential to minus 180 degrees axis. It's clear from here. It's a type 1 system which will be tangential on this side to minus 90 degrees axis and on this side to minus 180 degrees axis. So this becomes the phase plot for me for this particular system. I hope this is clear. As far as uncompensated system is concerned, I have got the gain plot and the phase plot, the Bode plots, that is the semi-log paper plots I have got. Now let me see the phase margin of this system. I have got the data in my notes. The phase margin in this particular case is equal to 15 degrees. So it is short by how many? By 25 degrees, you see. I need 40 degrees and this is 15 degrees, so it is short by 25 degrees. Now you see the adjustment, please. As I told you, if you get this example very well, the procedure will be well set. Now what I can do, you see that this is your plot of the lead compensator, and if I cascade a lead compensator, the two plots will get added up because of the Bode characteristics. Because of the Bode characteristics, you see, the two plots will be added up. Now you please notice this point very carefully. What I can do is that place this, please, you are disturbing me. Gentlemen, you are disturbing me, please. My attention gets diverted. Don't speak, please. This omega m is the frequency. So this particular thing, this magnitude, I want to have this phase lead. this phase lead I can place at this particular point, please. You can just see this phase lead I can place it. So it means what I can do is that this omega m can coincide to this point, with this point, and I can design my system in such a way that phi m is equal to 25 degrees, my phase margin will be realized. Anyone who can think of the problem involved in this, please? Think of the problem involved in this. Phi m, I am placing phi m here. The maximum phase value is equal to 25. In that particular case, the net angle at this particular point will become 40, which is the desired phase margin. But I envisage a problem. If I do this, I fear that the phase margin will be less than 40. The reason? Could you think of the reason, please? Yes, please see that. You see that when you are adding this phase at this particular frequency, you are adding the gain as well. And if you add the gain to this, the crossover frequency is getting shifted to the right. That is also sure, to the right, not to the left. That is also set, you see, that if you add phi m at this particular point, the magnitude gets added to it and the crossover frequency gets shifted to the right. What is the consequent effect? The consequent effect is this, that because at the, suppose it gets shifted to this point, tentatively let us say, you have calculated your 25 degrees hoping that the uncompensated system is providing 15 degrees to you, you see. But now since the crossover frequency gets shifted, the contribution of the uncompensated system has reduced from 15 degrees to the value you do not know, you see, exactly you do not know, but it's a trial and error design. You can approximate it roughly to 5 to 10 degrees.
So in this diagram, haven't you marked incorrectly? It should be from the crossover.
Oh yes, I am sorry. Yes, you are very right. You are very right. Yes, I have taken the corner frequency here. This is 15 degrees. The gain crossover frequency of the uncompensated system is this, and you want, this is let us say 15 degrees. This will get shifted because of the addition of the total magnitude, and therefore the contribution of the uncompensated system will reduce. Okay, and this is the safety margin we will like to take beforehand, because its exact value I don't know beforehand. So if the safety margin you have taken does not work, the only thing is that you have to re-enter into the design cycle, and couple of trials will give you the final result. The guideline is this, that okay, 5 to, and you see the guideline is also provided by the open loop plot. If you see that there is a sharp fall off, so naturally larger margin should be taken. That's all. It's provided here. If the fall off is not that sharp, smaller margin will do, because after all it is this fall, it is this slope which is going to give you the idea as to how much the safety margin should be taken. But let us assume that I take a safety margin. In this particular problem I have taken a safety margin of 5 degrees. So what do? I require a phi m, the maximum phase lead of 30 degrees instead of 25 degrees, hoping that this shift will give me the final phase margin at least 40 degrees. This is, with this hope I am giving an additional phase angle of 5 degrees here. Okay, and therefore I can say the phi m, the required phase lead, is equal to phi s, the required phase margin, okay, or phi pm, you can say, we have used pm, required phase margin, yes, minus phi 1, the phase angle of the uncompensated system, plus epsilon, the safety margin. Will it do, please? Phi l, phi m, the maximum phase angle I require, is equal to the required phase margin minus the phase angle of the uncompensated system plus the safety margin. That is why I am writing here 40 minus 15 plus 5 equal to 30 degrees. Okay, so this 30 degrees of phi m I require, and hence I can get the value of alpha now. You see, one parameter is set. You will see from this design, the statement I made, the frequency domain design is very powerful, because the type of trial and errors you made in the root locus design, that much trial and error is not involved here. So you see, by this adjustment of phi of this phase angle, you have got one parameter alpha of your component. K you have already got from kV. Now alpha I get equal to 1 minus sine 30 divided by 1 plus sine 30 is equal to 0.334. This is the value of alpha I get. The only parameter left is tau. Now, well, if anyone has got an idea how to fix up tau, please. Yes? Omega m should coincide with omega gc. But which omega gc? This omega gc.
The new one.
The new one. How do I know what is the new one?
By shifting 10 log
The
1
slope
by
by plus 20.
That's perfectly all right. No, not 20. This value 10 log 1 by alpha. Because at the maximum phase angle, it is 10 log 1 by alpha. Please see. This much of magnitude would be added at omega m. This point may please be noted. And see the value 10 log 1 by alpha is 4.8 dBs. 10 log 1 by alpha equal to 4.8 dBs. So what should be the point? So I envisage that the new crossover frequency will be at the point where the uncompensated system has a gain of minus 4.8 dB, because 4.8 will be added to it. So this is the new gain crossover frequency, please. The uncompensated system should have minus 4.8, so that when 4.8 gets added to it, it will cross the 0 dB axis, and this will become my new gain crossover frequency. And hence now I think you have got the clue. The uncompensated system plot is already with you. So you read off this point at which the magnitude is minus 4.8 dB. As per my notes, it is 4.6 radians per second. Okay, so I now get the value of tau from this expression, that let omega m is equal to 1 by tau into 1 by alpha tau under the root equal to 4.6 radians per second. This will give me the value of tau parameter, get the value of tau, and the ds, the final result now I am giving you, turns out to be 0.376 s. So this is naturally the value of tau, you see, 0.376 s plus 1 divided by 0.128 s plus 1 is the value of ds I obtain. Okay. Now you may say that I have to tell you what from the point of view of examination also. Don't leave your answer like this because you have made a guess. You do not know whether that guess was satisfactory or not, and therefore you make a compensated plot, at least couple of calculations to check the phase margin for KGS-DS. This is the system now. What is the system? K was 12. 12 into 0.376 s plus 1 divided by s into s plus 1 into 0.128 s plus 1. This becomes your open loop compensated system, open loop transfer function of the compensated system. So now I think I need not make a sketch over here, I can proceed further, because for this particular system you can now make the Bode diagram and get the phase margin. Please note, entire phase angle curve will not be required. You just see the corner frequency, the cutoff frequency is it equal to 4.6 which you have calculated? If yes, calculate the angle, that gives you the phase margin. So you have to optimize, you see. Don't curse me later if the problem turns out to be lengthy. You have to optimize on the time. You have to see what is the total effort you require in solving such a problem. Okay, don't make an effort more than that so that you can evenly distribute the time. Okay, so in this particular case, for example, a check is required. Now you need not give the second trial, but at least you should say that look, your epsilon value turned out to be wrong, and you will like to do it now by taking epsilon larger. If phase margin turns out to be more than 40 degrees, there is no problem. 42 degrees, 43 degrees, it is fine. And if it is 1 or 2 degrees less, then also there is no problem, because after all, even 40 degrees is a guideline for us. Only the extensive simulation will tell whether the performance is satisfactory or not. Okay, yes please.
So if the requirements are given as kV and phase margin, why can't we take a larger phase margin, say try out for 50 instead of 40?
That is right.
Definitely ensure 40.
That is right. Okay, please see that he says that if the requirement is greater than equal to 40 degrees, then why not 50 degrees, 60 degrees or larger phase margin? Please see that in this case, what is the price you are paying? You have yourself said that the crossover frequency will shift. This crossover frequency is an index of bandwidth. The larger this value, the larger is the bandwidth. So it means there is a bandwidth limitation. You see, you cannot, ideally speaking, the bandwidth should be infinite, but the noise filtering requirement may put a limit on the bandwidth. And secondly, larger phase margin may impose some other restrictions also. Okay, bandwidth is one of the important things you can keep in mind. So you see that when the constraints, when certain specifications are given, we normally try to meet these specifications on the boundary so that margin for any other requirements is available. In this particular case, bandwidth is the right answer. So here actually I have not given you the complete problem. I simply say that any bandwidth requirement can be checked using Nichols chart. So let me now transfer it on the Nichols chart. You can see that a Nichols chart may be required if the problem is asking for bandwidth, because you cannot think of getting the bandwidth from the Bode plot. No, though you know that this crossover frequency is somehow an index of bandwidth. Larger this value, larger will be the bandwidth, but still the absolute value of the bandwidth you cannot obtain. You will have to make the closed loop frequency response, or you will have to use the Nichols chart to get the intersection with the 3 dB contour. That is the value of the bandwidth. So if the bandwidth is not satisfactory, you see, if the bandwidth turns out to be, if suppose now his question may be please taken care of. If the bandwidth requirement is too large, you can accommodate larger bandwidth. In that particular case, you can re-enter the design and take a larger phase margin. No one prevents. Larger phase margin is better, provided your other requirements are also satisfied. So entering into design cycle depends upon the total requirement you are going to take care of as far as the requirements of the user are concerned. Okay. So I think I can leave the lead compensator design problem here, hoping that the complete design procedure is clear. It's very simple design procedure. The trial and error is in terms of only epsilon, and to see whether your bandwidth requirement is satisfied or not. Naturally, you will make one trial from the examination point of view, but you should know the procedure, and hence I will definitely like the comments to be made at every stage. You have to convey, you have to give the message to me very clearly that if you were required to enter into the design cycle, you have the necessary knowledge for that. That is your responsibility to convey it properly.
Sir, could you repeat what checks are to be made once we have made a first iteration?
Once we have got DS, first of all I will like to check the phase margin. That is my check on epsilon. Because after all, these are the analytical calculations I have already done. I have even in these calculations, I have even not taken -3 dB into account maybe. So first of all, I like to check whether the phase margin requirement is satisfied or not. And I am telling you, you have not to stretch for 40 degrees. Anything around 40 degrees is acceptable. Once this is done, it means KV and phase margin requirements have been satisfied. Then if the problem or the user gives you the requirement on bandwidth also, translate this data on the Nichols chart, the magnitude and phase, not of this, of the compensated system. First make the Bode plot and phase angle plot of the compensated system, translate this data on the Nichols chart and get its intersection with the -3 dB contour to get the value of the bandwidth. If it is satisfied, your design problem is complete. If not, comment on it appropriately as to what will be your next design trial. Whether you will like to increase epsilon, reduce epsilon, what you are going to do, that you have to comment on properly. Okay. Any question on lead compensator design, please? Next I am taking the LAD compensator.
If you cannot satisfy both the bandwidth and the phase margin simultaneously.
You see, in that particular case, it means your requirements cannot be satisfied. That, as we did in this case, the lead cascade will also come to satisfy both the requirements simultaneously. If you are not able to satisfy by one unit, it means the complete lead as well as lag unit may be required. Okay.
And so we work with the asymptotic plot only.
No, I am making that here. If you are working with the asymptotic plot, I don't mind, provided you have taken enough care that your final check will give me the required phase margin. It is fine if you think that you will take asymptotic plot, but sufficient margin on epsilon, but don't make it too much. Suppose you take epsilon equal to 20 as was suggested by him, then the bandwidth requirement may not be satisfied. It is up to you whether you make an asymptotic sketch or you take care of the errors also. I don't think making errors is a big thing because no calculation is involved after all. Okay, no calculation is involved there. You can incorporate the errors and make the actual plot immediately. Okay, right. Now I go to the lag section or the lag compensator. You recall from the root locus sketch, what was our lag compensator? A pole here and a 0. Close bar. So if I take it ds could be written as, yes, in what format we should take? Let me see. Tau s plus 1, I am taking in this format. Tau s plus 1 over beta tau s plus 1. Naturally, in this particular case, beta will be greater than 1. You can just, the constant k, similar argument I am not using here. The k has been transferred to the uncompensated system. So this becomes the transfer function of a lag network or a lag compensator. Tau s plus 1 divided by beta tau s plus 1 with beta greater than 1. Let me see its frequency characteristics. Similarly, the frequency characteristics I am going to use. So up to the, what will be the first corner frequency, please? Omega is equal to 1 by beta tau first. And how about, this is a pole. Since it is a pole, I am making minus 20 dBs per decade here. And then a 0, plus 20 dBs per decade. So naturally it becomes 0 dB here. And I have here omega equal to 1 by tau. So this is omega versus dB. Omega versus dB. Now let us see the phase angle, please. Phase angle in this particular case, obviously, as you see, the angle will be lagging because beta is greater than 1. So let me take a sketch over here. Omega phase angle is lagging here. Okay. Now here, before I go ahead, though the calculations for this is 0 degrees, though the calculations for maximum phase lag and the frequency at which it occurs can be made. This magnitude, let me write first quickly, 20 log beta, it can be checked. Though these calculations can be made, but let me make one comment over here. The lagging characteristics of the network will not be utilized for compensation. Rather, it is a drawback, and we will like to see that the lagging characteristics does not give negative contribution to the system. What I am going to use, I am going to use this particular negative magnitude of the lag network for compensation, and hence I am not interested in marking phi m and the corresponding frequency here. This point may please be noted. This region of the compensator is not going to effectively contribute to the compensation I am going to take up, and therefore these magnitudes I am not taking. Now let us see how do we handle such a situation. I am claiming that the phase lag, it is called lag compensator because of the phase lag network, but in frequency domain design the lagging characteristics will not be utilized, as you will yourself appreciate when I take a numerical problem. I think I can straight away go to the problem and keep this characteristic in mind, and we will use this magnitude characteristics to get the appropriate value of the phase margin and the bandwidth or other requirements if imposed. I take a problem here. GS, this is not working. GS equal to K over S into S plus 1 into S plus 4. The problem we had taken up in the tutorial class. Okay, now in this case, let me say that Gj omega I want to get in time constant form. So it is K by 4, it is J omega plus 1, 0.25 J omega plus 1. For this problem, it is given that I require the phase margin equal to 43 degrees, I require the bandwidth equal to 1.02 radians per second, and I require kV greater than equal to 5. These are my requirements. My design procedure will be same. I will first satisfy the kV requirement by assigning suitable value to k. Then I will take care of the phase margin. After that I will go to the Nichols chart to check the bandwidth. If it is not satisfied, I will re-enter with appropriate knowledge obtained from the Nichols chart. tuning or readjusting knowledge will be given by the n== chart as to bandwidth is large or small, whether I can play with this, and if, as the question was there, if all the requirements cannot be satisfied, then a lag section and a lead section together will meet my requirements on phase margin and bandwidth. Okay, so now take up, yes, please help me, what is K equal to? K is equal to 20 and KV is equal to 5 naturally will be given by that. So is it okay, please? So in that case, I write Gj omega uncompensated system. Since K has been clubbed with the uncompensated system, it is 5 over j omega plus 1 0.25 j omega plus 1. Come on, make a sketch, please. I am making asymptotic here to save time, but you can use the errors as well. So this is 1 minus 20 dBs per decade. One corner frequency omega is equal to 1 and one more omega is equal to 4. Omega is equal to 4 here, omega is equal to 1 here, and I have the corresponding phase angle plot here. Help me please, what are the asymptotes? I think you will recall the asymptotes we had taken for this, minus 90 degrees and minus 270 degrees. So let me draw a line for minus 90 degrees here, a line for minus 270 degrees here, and a suitable curve will come. Let me see what is the phase margin. So accordingly I will plot the curve over here. This is the phase angle I make for this particular system. Minus 90 minus tangent inverse omega minus tangent inverse 0.25 omega. I can write here minus 90 minus tangent inverse omega minus tangent inverse 0.25 omega. This becomes my phase angle curve. This is the gain crossover frequency, and at this particular point I find the phase margin to be minus 4 degrees. So it means for this particular K value, which you have taken equal to 20 degrees, which meets your steady state requirements, the system has become unstable. However, when I add a compensator, the stabilization naturally will come. The phase margin in this particular case turns out to be minus 4 degrees. See that this is dB on this side and omega, here it is omega and phase angle. Now make the adjustments please. I think take up this sketch and see what type of adjustment I am going to make in this case. If you look at this red line, which is the phase angle curve, please see if I am able to pull the low frequency region down, it is possible to increase the phase margin, isn't it? If I pull the low frequency region down so that the crossover frequency, the gain crossover frequency shifts on the left, okay, then the phase margin will be improved, will be increased. One observation here itself should be clear, that the lag compensator will always reduce your bandwidth, while the lead compensator is going to increase your bandwidth. Is it alright please? Because with the lag section you are pulling this down in the low frequency range. It means the gain crossover frequency is reducing, and I told you that the gain crossover frequency reduction leads to reduction in bandwidth, increase leads to increase in bandwidth, and therefore the lag compensator is going to reduce the bandwidth while the lead is going to increase the bandwidth. This point may help you in taking the decision whether for a given design problem you are going for a lead compensator or a lag compensator. Check the bandwidth of the uncompensated system. If you find that the uncompensated system bandwidth is with respect to the required bandwidth, you see, increase or decrease you can find. Not that if the increase is required you cannot go for a lead compensator. You can see that if increase, then will it approximately lie within the range required. Please see that it's not an absolute answer, that uncompensated bandwidth you will see, if the required bandwidth is larger go for the lead, if it is smaller go for the lag. No, you have to see, you simply know that your lead compensator will increase the bandwidth. After the increase, is it expected that it will lie within the acceptable range? If it is expected, you can try the lead compensation. Similarly, the decrease, if it is expected that after the decrease it will still lie in the specified range, you can go for the lag compensation. So it is only the guideline, and suitable guidelines you have to take You have to suitable clue you have to take from here as to your trial is going to be a lead compensator or a lag compensator. So in many cases, if both the phase margin and the bandwidth requirement is not satisfied, what you do in that case? First you design the lag section, because lag section will meet your phase margin requirement, and then you add a lead section to meet the bandwidth requirement, because the lead section will increase the bandwidth. So you can really, in that case, one can divide the phase margin requirement to be compensated. You can split that into two parts, because you know that the lead compensator also provides a phase lead. So you can really split the requirement of the phase margin into two parts. Let us say you require 60 degrees. If you require total, if you compensate it total by lag compensator, what will happen? The gain crossover frequency will have to come deep into this side. It means actually the bandwidth will be drastically reduced if you compensate it total by the lag section. But if you say, okay, I will require a lag section only for 30, so what will happen? It will slightly go down for 30. So 30 degrees phase margin can be obtained by lag compensator. Remaining 30 degrees, you treat the lag compensated system as an uncompensated system for the design module of lead compensator and provide an additional phase margin of 30 degrees. Your the gain crossover frequency will also shift, and hopefully the bandwidth requirement will be met. It's a trial and error procedure. You try and get the values of both lead and lag. So the standard, you see, you will recall in the root locus section, our practice was to first design the lead section and then go for the lag. Okay, that is, first you meet the transient response and then you design the lag section so that it does not disturb your root locus plot. Here it is this way: you first design the lag section, partially meeting the phase margin requirement, slightly decreasing the gain crossover frequency and hence the bandwidth. Then design the lead section, meeting the remaining phase margin requirement and hopefully increasing the bandwidth to the desired value. Okay? Therefore, now I switch back to the lag section procedure. Now you can help me please. What shall I do? Now you just see that if I take, you see, let me first of all get the frequency at which the phase margin is how much? I need 43 degrees. Let us say that this is the cutoff, or this is the gain cutoff frequency at which the gain crossover frequency at which the required phase margin of 43 degrees will be obtained. Is it all right? This is 43 degrees. So now what do you want? You want this particular plot to be shifted down by this much of dB. I need your attention please here. This much of dB, the idea should come from you. This much of dB if I add, because it's a log plot, it can be added, so that the total plot comes down, the crossover frequency is given by this point, and hence a phase margin of 43 degrees will be realized. Let us say that I match this frequency at this particular point. Intuitively I am saying, what are the problems involved in it? If I match this, I will like to put it at this point. Why? And not at this point? Because let me give the maximum attenuation at a time, you see. Why do I give the partial attenuation? This is the maximum attenuation possible. This is the maximum dB by which I can bring it down. So naturally I will be interested in this region. The only thing is this, that this region extends from omega is equal to 1 over tau to infinity. So what point should be taken? That is important. Can you give me some clue here? What point should be taken? I mean, you give me some qualitative idea. Should it be omega is equal to 1 over tau? Or should it be very, very large value? Or it can be anything. That is the idea I want. What could be what is the reason? Why twice?
So we don't want it to be very large also.
Why?
The bandwidth will reduce.
Okay, let us see. The idea is fine. But with respect to the phase angle, you just see, please. You know that again you have taken 43 degrees without the contribution of the phase lag. In this case it's a lag, it's a negative contribution. So let us say if you take at this point, this much of phase lag will be added. So it means the 43 degrees which you have taken, you will not be able to obtain 43 degrees, it could be 35 degrees. So one thing is there, that you 30, even less, you see. My plot is not accurate. So at the corner, it's a substantial phase lag at the corner frequency, you see. My plot is not to scale. It's a substantial phase lag at the corner frequency. So the clue could be that why don't you take it very far away? If you take it very far away, in that particular case, what will happen? The value of omega, in this particular case, it will be there, but 1 over tau and 1 over beta tau, which you are going to realize using RC components, the components you will not be able to get appropriately. It is the realization problem that you want, that 1 over tau and 1 over beta tau should be proper, and that demands that 1 over tau should not be taken very far away, because in that particular case the realization problem comes. And there are no quantitative guidelines. The qualitative guideline is this, that if this particular point at which it is 43, first of all, instead of 43 degrees you take it 43 degrees plus epsilon. Assume that some phase lag will be anyhow added. Assuming this phase lag here, you take it 43 degrees plus epsilon, and in this particular case, let us say in this particular problem, I have taken that epsilon to be 12 degrees. So it means I want to take a point at which it is 55 degrees and not 43 degrees, and I find that point in my notes. That point is given as 0.52 radians per second. So please note, first of all, I have taken care that the safety margin should be taken for this phase lag, and this, again, there is no quantitative guideline. You have to get appropriate value by trial and error. Okay, so very large value for the obvious reasons should not be taken, because your bandwidth will reduce drastically. So in this case 12 degrees I have taken because this is the final design, and 55 degrees, the corresponding value is 0.25. The qualitative guideline is this, that this frequency should match approximately the frequency which is this 1 over tau you have taken, or this particular point you have taken. You place this particular point about 2 octaves below this particular point. You see this point, please, 2 octaves, that is, you take it divided by 4. This is again just qualitative guideline. It may or may not work, but mostly it works. This is 0.25, so it means you place this frequency which is the corner frequency 2 octaves below this point. So this point you already know, this point is 0.52. Now you have got the answer. The answer is this, that 1 over tau equal to 0.52 by 4. That by 4 is a qualitative guideline to you. You may like to take 1 decade below, different guidelines depending upon the problem, depending upon your experience. You see, if you are working with the CAD software, you may try different viewpoints, but the procedure should be well set. So I take 2 octave in this example in this to give you some numerical answers. So I take now 1 by tau is equal to 0.25 by 4, and therefore one parameter is set in this particular case. Now how about the other parameter? Help me please, how do I get the other parameter? The other parameter should come from this. Please see, this much of attenuation, this much of minus dB you want, and this much of minus dB should equal this value. 2 octave below you have already taken. So this point is already available to you. What is this point? Let me take. It is 0.13. Oh, it was so obvious. It is 0.13. Okay, it is 0.13. So at 0.13 you read off the value, and this, as per my notes, is equal to 20 dBs. Okay, so it means you want this much of attenuation, and therefore I get the other parameter, 20 log beta should be equal to 20, which gives me beta equal to 10, and hence both the parameters are available. The total design in this case is ds is equal to 7.7 s plus 1 divided by 77 s plus 1, with beta and the other parameter available to you. And now all the other comments are identical to the first case. That is, you cascade your ds to the uncompensated transfer function, get the Bode plot of the overall system and see that the effect of the phase lag is that is the value of epsilon has been appropriately taken, and you are able to get the required phase margin of 43 degrees, around 43 degrees with the value of epsilon we have taken. And one more check, and that check is that of gain crossover frequency. The check is that of bandwidth. If there is a slight variation required in the bandwidth, in that particular case maybe by adjusting epsilon you may be able to meet. But if there is a big gap between the bandwidth you have acquired and the bandwidth desired, then it is an indication that whatever design you have made, treat this design as an uncompensated system and go ahead for the lead section, so that the total lag lead compensator is available to you. And I think with this, through these examples, I have conveyed the procedures, and I hope the procedure should be clear. And with this, we close our discussion of this particular course. Thank you very much for your cooperation.